Hey guys, in this video I will cover almost everything about LTE physical layer and LTE air interface. These two topics are most difficult topics to understand, but I will try to make things as easy as possible. Here is breakup of the topics. We will understand what is OFDMA, what are its advantages and disadvantages, LTE frame structure. We will talk about both types of frames, type 1 for FDD and type 2 for TDD. LTE resource grid to understand concept of resource block, resource element, and cyclic prefixes. We will calculate LTE slot duration to show that how its value is 0.5 millisecond. We will calculate LTE data rate in downlink. We will study downlink physical signals, their importance, and see how physical signals are arranged in resource grid. In the end, we will understand SCFDMA for uplink and see how it is different from OFDMA. So, here we go. In LTE, modulation technique used in downlink direction is OFDM, means orthogonal frequency division multiplexing. For uplink, modulation technique is SCFDMA, single carrier frequency division multiple access. Both OFDM and SCFDMA are multi-carrier technologies. But before explaining OFDM and SCFDMA, I will first talk about conventional single-carrier technologies to understand what were the problems with single-carrier technologies. Then only we can understand how OFDMA and SCFDMA have solved those problems. Till date, cellular systems have used single-carrier modulation schemes almost exclusively. But single carrier modulation has got an inherent problem, that is, inter-symbol interference or ISI. Let me explain this phenomenon. When radio signal comes from tower to mobile in downlink direction, it does not take single direct path for reaching the mobile. Rather, multiple components of the same signal reach to the same mobile because of the multiple reflections from surroundings. The component that is in line of sight of tower reaches to the mobile earliest, and the rest of the components are delayed by varying degree, depending on the path taken by them. When these multiple components of same signal are combined at UE, sometimes constructive interference and sometimes destructive interference takes place. This figure shows that receiver how delay induced by multipath propagation can cause a symbol received along a delayed path to bleed into a subsequent symbol arriving at the receiver via a more direct path. This phenomenon is referred as inter-symbol interference. There are many solutions available for minimizing this problem. For example, CDMA systems employ rake receiver to resolve ISI problems. But no solution can remove this problem completely. Moreover, situation becomes worse at high data rates when duration of each symbol is very small and data loss because of ISI becomes very prominent. Let's first understand what is OFDM. Then we will see how it solves problem of ISI. In OFDM, a large number of closely spaced orthogonal subcarrier signals are used to carry data on several parallel data streams. In other words, OFDM divides incoming high-speed data in multiple parallel low-rate data streams. Then each data stream is mapped to one of the closely spaced orthogonal subcarrier and is used to modulate these orthogonal subcarriers using varying level of QAM modulation, such as QPSK, QAM, 64 QAM, depending on the signal quality. So we can say each carrier in OFDM is independently modulated, and each OFDM symbol is therefore a linear combination of the instantaneous symbol on each of the subcarriers in the channel. Because data is transmitted in parallel rather than serially, OFDM symbols are generally much longer than symbols on the single carrier systems for equivalent data rate. Conceptually, OFDM is a specialized FDM. The additional constraint being, all the carrier signals are orthogonal to each other. There are two main advantages of this orthogonality. Crosstalk or interference between subcarriers is eliminated. And second is, inter-carrier guard bands are not required. Because guard band is not needed between two subcarriers, a lot of bandwidth is saved on air interface. Now let's see how OFDM resolves the problem of inter-symbol interference. There is one truly remarkable aspect of OFDM, that is, each OFDM symbol is preceded by a cyclic prefix, or CP, to prevent ISI caused by multipath delay spread. The cyclic prefix represents a guard period at the starting of each OFDM symbol, which provides protection against multipath delay spread. The duration of cyclic prefix should be greater than the duration of multipath delay spread, then only it can prevent ISI. LTE specifies both short and long cyclic prefix lengths. The short cyclic prefix is intended to be sufficient for majority of scenarios, while the large cyclic prefix is intended for scenarios with particularly high delay spread. Remember, the cyclic prefix is an overhead which should be minimized. Everything has got some limitations, and OFDM is no exception. OFDM has two principal weaknesses relative to single carrier systems. First is susceptibility to carrier frequency errors, or you call it inter-carrier interference. At the receiver, during demodulation process, received signal is mixed with the signal produced by the receiver's local oscillator. Ideally, the received signal strength and the receiver's local oscillator should have identical frequency. Unfortunately, this is not the case always. Transmitters and receivers' local oscillators will invariably drift. So there has to be some mechanism to keep them synchronized. Therefore, each base station periodically sends synchronization signals which are used by a receiver for synchronization. Apart from this usage, synchronization signals are used for other purposes such as initial acquisition and handover. The other major drawback of OFDM is a high signal peak to average power ratio, high PAPR. As I said earlier, the OFDM symbol is a combination of symbols from all the subcarriers. Subcarrier voltages can add in phase at some points within the symbol, resulting in a very high instantaneous peak power that is much higher than the average power. Because of this phenomenon, the instantaneous transmitted RF power can vary dramatically within a single OFDM symbol. A high PAPR reduces efficiency of the transmitter RF power amplifier. Because of this reason, to save UE battery, OFDM is not used in uplink direction. Let's now come to LTE physical layer frame structure. To support transmission in paired and unpaired spectrum, two duplex modes are supported: FDD, frequency division duplex, and TDD, time division duplex. The radio frame structure type 1 is used for FDD. It has duration of 10 milliseconds and consists of 20 slots with a slot duration of 0.5 ms. Two adjacent slots form one subframe of length 1 millisecond. If we go inside the slot, we can see there are 6 or 7 OFDM symbols inside a slot. If normal cyclic prefix is used, then number of OFDM symbols in a slot are 7, and if extended cyclic prefix is used, then number of OFDM symbols in a slot are 6. Frame structure type 2 is applicable to TDD. Each radio frame of length 10 ms consists of two half frames of length 5 ms each. Each half frame consists of 5 subframes of 1 millisecond. The supported uplink and downlink configurations for TDD are listed in this table. Note, for each subframe in radio frame, D denotes that subframe is reserved for downlink transmissions, U denotes that subframe is reserved for uplink transmissions, S denotes a spatial subframe with 3 fields: downlink PDS, GP, and uplink PDS. The spatial subframe consists of 3 fields: downlink pilot time slot. This field carries synchronization and user data as well as downlink control channel for transmitting scheduling and control information. Second is GP, means guard period. Third one is uplink pilot time slot. This field is used for transmitting the PRH and sounding reference signal. These 3 fields are individually configurable in terms of length, although the total length of all 3 together must be 1 ms. Now let's understand the concept of radio resource allocation in LTE. The smallest element of resource allocation that can be assigned by the base station scheduler to a mobile is called physical resource block. So we should first understand what is a physical resource block. A PRB is defined as a group of 12 consecutive subcarriers for one slot duration of 0.5 ms. For normal cyclic prefix, one subcarrier has 7 OFDM symbols for a duration of one time slot. So in one time slot, 12 subcarriers will have 12 into 7 equal to 84 OFDM symbols. For extended cyclic prefix, one subcarrier has 6 OFDM symbols. So for a duration of one time slot, it will have 12 into 6 equal to 72 OFDM symbols. Figure shown here is also called resource grid. Each box within this grid represents a single subcarrier for one symbol period and is referred to as a resource element. Note, in MIMO applications, there is a resource grid for each transmitting antenna. Let's do some mathematics now. Sampling frequency for 20 MHz channel bandwidth is 15 kHz into 2048, where 2048 is FFT size. So it will come out to be 30.72 MHz. As sampling time is reciprocal of sampling frequency, sampling time is 1 upon 15 kHz into 2048. This is the time gap between 2 samples. Note, sampling frequency 30.72 MHz is 8 times of the sampling frequency used in UMTS, which is 3.84 megachips per second. It has been done to maintain the backward compatibility with the UMTS. Now we will calculate the time duration of a slot. As we know, for normal cyclic prefix, there are 7 OFDM symbols and 7 cyclic prefixes. Duration of a time slot should be duration of 7 OFDM symbols plus duration of 7 cyclic prefixes. Remember, thumb rule of OFDM is that length of OFDM symbol is inverse of carrier spacing. For LTE, carrier spacing is 15 kHz, so OFDM symbol duration will be 1 upon 15 kHz, that is 6.67 microseconds. Duration of cyclic prefixes are, for short cyclic prefix, 144 into TS, where TS is the sampling time. For long cyclic prefix, it is 512 into TS, where TS is again sampling time. Let's put all these values in the formula. Slot duration would come out to be 4.6 milliseconds. But we already know slot duration is 0.5 millisecond. So where is the gap? Here's the answer. Interestingly, very first CP in each slot is bigger than rest of the CPs. When a small CP is used, size of first CP is 116 TS. So let's update above formula and calculate slot duration again. This time it will come out to be 0.5 millisecond. So what is the conclusion? Conclusion is that first CP is always bigger than rest of the CPs, and rest of the CPs are equal. Let's quickly calculate the LTE data rate. I'm saying quickly because I will make a separate video on this topic. Here we will just take only one case. 20 MHz channel bandwidth has 100 resource blocks. One resource block has 12 subcarriers. One subframe is of 1 millisecond. One time slot has 7 OFDM symbols when normal CP length is used. One OFDM symbol has 6 data bits when 64 QAM is used as modulation scheme. Therefore, number of bits in a subframe are 100 resource blocks into 12 subcarriers in one resource block into 2 slots in a subframe into 7 modulation symbols in a slot into 6 data bits in one OFDM symbol. It will come out to be 100800 bits. Hence the data rate is 100.8 Mbps. If 4x4 MIMO is used, then the peak data rate would be 4 into 100.8 Mbps, that is 403 Mbps. If 3x4 coding is used to protect the data, we still get 0.75 into 403 Mbps. That will come out to be 300 Mbps approximately. Next thing to discuss in downlink are physical channels and physical signals. In this video, I will not discuss physical channels because it is a very big topic. I will cover this topic in a separate video. So now let's discuss physical signals. Downlink physical signals do not convey information to or from higher layers. There are 2 types of physical signals in downlink. First is reference signals. Reference signals are used to determine the channel impulse response, or we denote it by CIR. In other words, they are used in LTE to facilitate carrier offset estimate, channel estimation, and timing synchronization, so that coherent demodulation can take place at receiver. In order to successfully receive a MIMO transmission, the receiver must determine the channel impulse response from each transmitting antenna. In LTE, channel impulse responses are determined by sequentially transmitting known reference signals from each transmitting antenna. We must get an accurate CIR from each transmitting antenna. Therefore, while one transmitting antenna is sending the reference signal, other antenna is idle. Once the channel impulse responses are known, data can be transmitted from both antennas simultaneously. Note that reference symbols are transmitted every 6 subcarrier. Further, reference symbols are staggered both in time and frequency domain. Overall, there are 510 unique reference signals possible. A specified reference signal is assigned to each cell within a network and acts as a cell-specific identifier. When UE tries to figure out downlink power, it measures the power of this reference signal and takes it as a downlink cell power. Second type is synchronization signals. Synchronization signals use the same type of pseudo-random orthogonal sequences as used by reference signals. These are classified as primary and secondary synchronization signals depending on how they are used by UE during the cell search procedure. We will discuss more about synchronization signals while studying cell search procedure. Let's talk about uplink transmission now. As we know, power consumption is a key consideration for mobile terminal. OFDM cannot be used for uplink transmission because of high PAPR that leads to poor power efficiency. The LTE physical layer uses single carrier frequency division multiple access as the basic transmission scheme for the uplink. The principal advantages of SC-FDMA over conventional FDMA is lower PAPR. SC-FDMA is a misleading term since SC-FDMA is essentially a multi-carrier scheme that reuses many of the functional blocks included in the UV OFDM receiver signal chain. So many things are common, so many blocks are common between OFDM and SC-FDMA. The basic transmitter and receiver architecture is nearly identical to OFDMA, and it offers the same degree of multipath protection as offered by OFDMA. Thanks, guys.